Great, thank you very much, and thank you for inviting me. It's a real pleasure to be speaking on this occasion. I first met Akshay about a little over 20 years ago when I spent 2 years at Princeton, and he was part of an outstandingly, in fact, almost frighteningly talented group of graduate students, if I remembered exactly what his status was at the time, who came along to graduate courses that I gave, although I claim absolutely no credit for his subsequent achievements. But anyway, it's, as I say, a real pleasure, and also a pleasure to be able to respond to his very interesting, I don't know if this was part of my brief, but it certainly seemed a natural thing to do, to respond to the essay that he recently wrote, which I'm sort of assuming, although pretty well everybody will have read, although not assuming in the sense that it's a prerequisite for what I say, but just sort of, I'm guessing that you probably have. But let's just remind ourselves what he was talking about. So the main theme was what might happen if you had a program a bit like AlphaGo, that you just fed it a few basic mathematical facts, and then it just developed, just as AlphaGo developed just from the rules of Go, all the sort of strategies and things needed to play incredibly well, and much better than human beings. What if you had something like that for maths, where you fed it a few basic facts and it then developed the kind of competence to prove very, very difficult theorems? Of course, a lot of people have thought about that question, and at the moment it seems as though the problem is that whereas with a game you have a very clear reward function, you end up winning the game or you don't. With maths, it's much less clear what counts as the reward function. In fact, that brings us on to the next point, which is that actually focuses on a lot, which is what makes us assign value to mathematical statements, because anybody could produce a program that just churned out meaningless, boring mathematical statements one after another. You could just have a whole lot of statements of the form x equals x, where x is a more and more complicated term or something like that. But we want to somehow to say that to reward interesting statements, and I think nobody quite knows how to do that precisely enough at the moment for us to be able to develop a program that would just get on with maths all by itself. But nevertheless, it doesn't seem as though it's beyond the realms of possibility at some point in the next few decades. And so I want to discuss these themes, and sort of I also want to argue that assigning values to statements, well, actually I've just more or less argued it, is an essential part of doing mathematics. It's not, you can't really divide the process of mathematical research into two parts. One is finding proofs, and the other is evaluating and deciding what's interesting. I think the two go very, very closely together. Just a couple of words about what I won't be talking about. So I don't want to start talking about whole areas of maths being more interesting than others, because partly I don't find that very pleasant, and partly because that's just not the theme of this talk anyway. People have different views about what's interesting and so on, and there I think that can be just a matter of taste. I think some people prefer certain sorts of maths and other people prefer other sorts of maths, and it's very, very good that we have people doing, it's very good that you have those differences in taste, so that people will specialize in different areas and we can make progress on lots of fronts all at the same time. So I'm talking much more about what makes a statement interesting if you accept that the area which surrounds it is interesting. The other thing is that I'm not really, although the alpha zero or aleph zero, whatever idea that actually talks about was probably more to do with a machine learning program like AlphaZero or AlphaGo or whatever. I've thought quite a lot over the years about much more traditional forms of automatic theorem proving, which I'm going to talk a little bit about later on. What would be needed for that? So I like the idea of a program where you really understand how it finds proofs. I like that much more than the idea of a program that's just a black box that spits out a proof that might not be a very nice proof at the end, but it just guarantees the truth of a statement or something like that. And I think I unfortunately was not able to attend Melanie Mitchell's talk yesterday, but I would guess that I've read a lot of what she's written, and I feel very much in sympathy with what she says about those kinds of things. One other thing I want to say before I get going properly, when I say this is a response to Akshay, that word sometimes has overtones of disagreement. You know, you say this, but I'm going to respond by saying, no, you're quite wrong. This is the case. This is not that sort of response. It's just more like some thoughts of mine that are provoked by what Akshay wrote, many of which are very similar to what he actually wrote. When I was thinking about what to talk about, I kept finding that things I wanted to say were basically there in what he wrote anyway. So that's just a way of saying that what he wrote kind of chimes with things that I've thought about over the years while thinking about automatic theorem proving. So that's two of the properties that Akshay really draws attention to that mark out interesting statements from less interesting ones, are whether they're difficult and whether they're central. And I think that's not too much to say there. I mean, obviously, if somebody comes up with a proof of a statement that many people have tried and failed to solve, then that's certainly makes it more interesting than if it was another statement that not so many people have tried to solve that came out quite easily. But difficulty on its own is not enough. One can think of very difficult statements that where one somehow feels that if somebody did manage to solve them, that wouldn't necessarily count as terribly interesting. And one of the features that marks out the sort of interesting difficult statements from the less interesting difficult statements is how central they are, how much they connect in some sense to other parts of mathematics. So I'm not going to try at this point to say too precisely what those are, but another point that Akshay mentions is that because mathematics is such a vast subject now, any individual tends only to understand and appreciate a really tiny fraction of mathematics. And so a lot of the judgments we make about which bits of maths are difficult and central are not direct judgments. I, for example, don't judge the Langlands program to be difficult because I've attempted to make progress on it and failed. I haven't attempted it at all. I don't even really understand, except in the vaguest terms, what it's all about. But I know of lots of famous mathematicians who have made small amounts of progress, well, small relative to the totality of the Langlands program, but those, because of other people have tried to do, a lot of other people have worked on those things, even what might seem like a small part of the Langlands program is celebrated as being extremely important and leads to awards and all kinds of things. So I get a sense of the importance of the Langlands program, not because of my appreciation of it, but because I observe the behavior of other mathematicians and listen to what they talk about, even if I don't really understand what they're saying. And the same is true of centrality. If I hear from experts in an area that one problem is central in the sense that if one could solve it, it would cause immediately a whole lot of progress on a lot of other unsolved problems, then I just believe what they say. But in my own area, I sense these things because I've actually tried them and because I appreciate some of these connections directly. The other point, another big point that Akshay makes is that if there were a big advance in automatic theorem proving, then it could well change. So it's not clear that it will affect the whole of mathematics immediately in the same way. There could well be some areas where that are easier to automate the proof finding in than other areas. And so then our assessment of what's difficult, it'll then become what's difficult modulo our wonderful theorem proving programs. And so our assessments of difficulties could change a lot. And so could our assessments of centrality for similar reasons. So I'm not really going to be talking so much about this social aspect of how we assign value. I'm going to try to argue that there are intrinsic features of problems that make them and statements that make them difficult and or central. But a few comments to make about any notion of difficulty and any notion of centrality. The most important is that difficulty is not just an absolute thing. You don't just have a function that takes mathematical statements to some measure of difficulty because, well, this is something you observe with humans, that a problem that's easy for one person will be very hard for another, for the simple reason that one person has some relevant background knowledge and competence and the other person doesn't. So there'll be problems that I can solve that with relative ease that a number theory, a sort of algebraic number theorist would find extremely hard, and vice versa. So difficulty always has to be relative to a given background. And I think the way to understand that is to think about the idea of mathematics as a huge body of knowledge that sort of develops incrementally. You have a kind of boundary, so to speak, and some sort of idea of what the next thing is that you need to prove beyond the boundary, or next things, because the boundary is long and there are all sorts of things just beyond it. But so something that is way beyond the boundary would be more or less impossible, but something that's just a little bit beyond it, that's somehow within reach, we use that phrase quite a lot, that we might regard, the difficulty we would assign to that would be relative to the kinds of other results that are on the right side of the boundary, that are the known side of the boundary, that are sufficiently close to it. So the whole thing is somewhat connected. I'll talk a bit more about this sort of model of how mathematics develops later on. So I want to talk about, just to give some examples of how I think, or why I think that, or what I think interest is, and why I think it's at least partly an objective property of statements relative to a given background, and not just some kind of aesthetic, woolly aesthetic thing that we humans sort of feel emotionally about theorems and so on. So the background for this that I'll assume is that you know, we have sort of knowledge that a student might have near the beginning of a first course in real analysis. So they'll know all about addition and multiplication and things like that. But they'll also have had a few basic definitions like convergence, continuity, and so on. So we will take those for, so we will take it that those are interesting somehow, and then let's see where we get. So once we've got those, we find that there are some questions that we can solve in a kind of what we would call a routine way, just given the basic definitions and basic knowledge of what a proof is. So there are three examples: that a composition of continuous functions is continuous, that if an is convergent, then and f is continuous, then f of an is also convergent, and that if f and g are continuous, then f plus g is continuous. So I now want to take a little tour of how a computer might solve this kind of problem, and I'll take the second one. So what I'm going to say now is based on a program that I wrote in I developed in collaboration with Mohan Ganisalingam. I hesitated there because he was the one who actually did the programming, but we designed the program together. And this was a program that could solve routine, or at least some routine problems in mainly in metric space theory, but sort of just basics of metric spaces. So the way we organized it, we organized our, so I'm not going to say exactly what the program would have done, but I'll just give you a kind of flavor of what it did. So we tended to organize our things that we wanted to prove by having a line, and above the line we would put what we were allowed to assume, and below the line we would put the thing that we want to prove. And so here we're allowed to assume that an converges to A, we're allowed to assume that f is continuous. There are a few more things, like I haven't told you what the domain and range of f are, but those of course were in the program. I'm just being a little bit less formal for the sake of this presentation. And that we want then to prove that f of an tends to f of a, or you could just think of f as a function from R to R. It wouldn't make much difference. In fact, maybe I've forgotten now. I think perhaps I am going to be thinking of f as a function from R to R. So the program would then proceed using just a very limited repertoire of proof generating moves or proof discovery moves. So I've highlighted the target here. I've got the statement below the line we called the target in red. That's because I'm just about to do something to it. What I'm about to do with it is expand it by using the definition of convergence. So I'm going to replace this by the epsilon. I want to call it epsilon delta, but there's only an epsilon here. Epsilon definition of convergence, or epsilon capital N or whatever. So when we expand it, we get this statement here. Yeah, so it is just the mod of f. So f is a function of r to r for this version. So that's changed the problem a little bit. What are we going to do next? Well, when we see a statement that we want to prove that begins with a universal quantifier, we have a very standard thing that we do, which we say we want to prove that something is true for all epsilon greater than 0. So we say to ourselves, let epsilon be greater than 0. We sort of fix an arbitrary epsilon and pretend it's not universally quantified over anymore. So I'm just going to do that. I just get rid of that universal quantifier. And now epsilon is some fixed real number. Because it's arbitrary, if I can prove it for that epsilon, then I'm done. Now we've got an existential quantifier in front of the first, as our first quantification in the target. That makes things a little bit harder. We actually have to choose something, and we don't know how to choose it yet. So what should we do instead? Well, we notice that if we expand f, we're going to start getting terms of the form f of x and that kind of thing, which gives us more of a chance of matching syntactically with what we have in the target. I'm sort of speaking in the language that the computer appreciates a bit more than a human. A human might say, well, we want to find something out about values that f takes, and expanding the definition of continuity will help us do that. So let's just do that. And that's gives us what you get when you just plug in the normal definition of continuous functions. And now we have universal quantifiers at the beginning, but that's above the line. So that's also a little bit tricky. We know that we can choose whatever we like for alpha and x, but we don't yet know what to choose. So let's just, however, sorry, in this particular case, that's all right, because there's some rather natural candidates for what to choose, because we have we need a positive real number to substitute for alpha, and there is a positive number floating around, namely epsilon. So it would be very natural to substitute epsilon for alpha. And similarly, we've got a real number a floating around, not quantified over, although you could say it's quantified over, but sort of much deeper up the statement. So it makes a lot of sense to see what happens if we plug a in for x. So I'm going to do both of those. So I'm going to replace x by a and alpha by epsilon, and I'll get rid of these quantifiers, and that's what results. And now I'm back in a situation where I can just get rid of something. So I'm told that there is a beta such that this holds. I don't know anything about that beta, but it's there. So I'll just say let beta be that beta, so to speak, and we can get rid of that. So now we're in this situation here. Now what are we going to do next? I'm highlighting rather a lot of stuff here. That's because I'm going to use modus tollens at this stage. So I know that I want to prove that fan minus f of a is less than epsilon. I know that for every y, in order to get fy minus f of a less than epsilon, it's enough just to show that y minus a is less than beta. So in particular, that's the case when y equals an. So it's sufficient, if I want to prove this target, to get that an minus a is less than beta. So let's just do that. So a lot's going to disappear at this point. I'm just warning you. And there we are. So we have that an tends to a, and we would like to prove this statement here. And you can see we're very, very close to home because that's more or less given to us. But let's just see how that happens. We expand that definition out. What shall we take for our theta? There's an obvious candidate, namely this beta. So let's make that theta be a beta. And at this point, we can carry on with that sort of process. We say we're given an m, it's natural to take for our n, that m that we're given. But actually, a simpler way of doing it is to say this statement is exactly the same as this statement, except that the bound variables have been given different letters. So we could just stop at this point, and I will, because I don't want to bore you with the really, really simple bits at the very end. But the main point the main takeaway from that is that I've just done some extremely routine steps and got to the end of the solution. And it was very interesting actually to find that with this program, what we found difficult to get a program to be able to do really correlated extremely closely with what was found difficult by undergraduates when they're doing elementary analysis, which has led me to this conviction that the notion of the difficulty of a mathematical problem is something that really has a lot of objectivity to it. It's not just a sort of subjective impression. It doesn't mean it's easy to say what it is exactly, but I think it's not impossible. So let's look at a question that would be quite a lot harder. And I'll maybe go a little bit faster through this one. I want to try to explain why this one is harder by going through a similar process, and we'll see that we'll get a little bit stuck at some point. So we'll start off as before. So we've got a function this time from 0, 1 to the reals, and it's continuous, and we'd like to prove that it's bounded. So as before, we'll expand a target. That's what it says for f to be bounded. There is some c such that all its values have absolute value at most c. What next? Well, it's not very obvious what to do with the bottom here. So instead, let's expand the definition of continuous and get the standard definition there. And now we've got really, the problem is not helping us all that much because we've got, there exists a c. We don't know what it is. We've got an epsilon and a y, and there's not really anything telling us what to choose for epsilon and y. So we have 3 things that we don't quite know how to choose. But in that situation, mathematicians often have a nice little technique, which in the computer science literature is called creating meta variables. And we would think of it as, let's just pretend we've chosen them, carry merrily on with our problem until, and then with any luck, we can sort of simplify it and then go back and make the choice later on. So that's what I'm going to do. Take those 3 things and just mark them as things that we need to choose later on. You have to be a bit more careful than I'm going to be about what's allowed to depend on what. I shall just be a bit cavalier about that. But of course, if you're writing a program, you can't afford to be. So now we've got a problem here where we're sort of pretending that epsilon, c and y are already chosen free variables when in fact they're not. And now we're in a nice situation again because we have, for all x something, we want to prove that for every x something holds. So we say, well, let x be blah, blah, blah. And here we want to show that there exists a delta. Sorry, we were given that there exists a delta such that this is the case. So we'll say, okay, well, let's let delta be that delta. So we'll get rid of those, but we'll be more careful this time. So I've specified here delta depends on y, and then actually there's something similar one needs to say about x, but I'll gloss over that a little bit. So we're now down to a problem like this. And so I'm not saying this is a good way of doing the problem, by the way. I'm just saying this is what an algorithm, sort of thing an algorithm would naturally do. So now we've got an x. So we've got something that we could consider substituting for z. So let's try that. So we end up with the statement y minus x less than delta implies fy minus f of x less than epsilon. And the next step, we'd like to match this with what we're trying to prove down here. So we'd like to get this to be in the form absolute value of f of x is less than or equal to something. And there are some details here, but we can get pretty close to it by transforming that into the equivalent statement that the size of f of x is less than the size of f of, it's not the equivalent statement, but that we get this statement from what we had before, and that would imply an upper bound for the size of f of x. And then we see that applying a big modus tollens again, that means that we'll be able to get the conclusion as long as x is within delta of y, and that this number here, f of y absolute value plus epsilon, is at most c. So this, with a little bit of easily automatable reasoning, we end up with two targets. We need to prove that y minus x is less than delta, and the size of f of y plus epsilon is at most c. And we're allowed to choose c, and we're allowed to choose epsilon. So getting the second one is easy, and we're allowed to choose y. So actually getting this whole second target is easy. But then getting the first target is not really possible at all. We'll just get that we need to prove that x is within delta y of y, and we simply don't have that. So we kind of got stuck. Although if we then examine quite carefully what we've done, we find that what we actually have observed is an important step in the eventual proof, which is that f is bounded in an open interval around y. And we were allowed to choose y. So actually what we've proved is that the function f is locally bounded, which is actually a very important step in the eventual proof. But somehow getting the next step from there requires somehow a bit more insight. And I'm going to switch it to human mode at this point. So that's where we've got to. Let me switch into human mode. So a human would expand the continuity definition, observe that we get this thing here. I'm just repeating the steps I've just been through, and get that f is bounded. Actually, my x is now playing the role that y was playing before, so that we've got that f is bounded on an interval x minus delta up to x plus delta. For each x, it's bounded on an interval around x. So we would naturally ask ourselves the question, does locally bounded imply bounded? So far, I think that's the program has sort of essentially done that. But the next step, I think, would be much harder. How would a human proceed from that point? I think it would be natural to do something like thinking, well, maybe it doesn't imply it. Let's try to find a counterexample. Let's try to find a whole bunch of intervals where it's bounded on each interval, but it gets bigger and bigger and bigger. And in order to do that, we're obviously going to have the intervals getting narrower and narrower. So we might naturally do something like what I've suggested here, that we have around each x, we have an interval between x over 2 and 2x. And then we need infinitely many of those intervals, at least to cover the open interval from 0 to 1. But if we allow ourselves, we then sort of notice that actually this doesn't quite work as a counterexample, because as soon as we cover 0, we've actually covered all the way up to some number. Oh, well, we haven't covered 0, but if we cover it with an open interval, then we've covered up to some theta or something like that. And then getting from theta to 1, we can do with only finitely many of these intervals. And so the whole attempted counterexample fails. And somehow once we've done that, that sort of gives us a feeling for what to do next in the proof. And we can do something like what I've sketched here. Perhaps I will not go through that in detail. But this is a kind of standard proof where we form the set of all y such that things are okay. And then we try to prove that we take its supremum, we try to prove that the supremum of the set of y is such that we're okay, because we can cover with finitely many of our intervals, is the whole, that supremum is actually 1. But the hard bit, I think, here is the idea of formulating or coming up with a realization that if of our intervals, if we could actually only cover with finitely many of those intervals, then we'd be all right. Once we've formulated that, which again, I'm not saying that's impossible for a program, but it's just definitely a different level of difficulty from the kind of thing I was doing when proving that continuous functions take convergent sequences to convergent sequences. Once we can do that, it then becomes a bit more routine again, though maybe not totally easy, but a bit more routine again to finish off the proof. Then once we've done that, let me go back to here. Once we've done that, then there's a sort of a natural process that humans will tend to go through, which is to say, we didn't care anything much about what those intervals were. We didn't care that they were intervals on which some continuous function is bounded. Actually, for this part of the proof, we just needed the fact that they were open intervals, and we needed to find, we had a certain number of them that covered the whole of 0, 1, and we just needed to find finitely many of them. So we do some process of abstraction, and that sort of interests us. We say, all right, there's a more general lemma there than what we actually needed for the proof. And then maybe some other time we need to prove that a continuous function on 0, 1 is uniformly continuous, or that it attains its bounds or something. And we then might find that precisely the same lemma comes up again there. At that point, we think, well, okay, this is quite a nice general statement that seems to have applications. And then we single that out as being an interesting statement. So this is what I want to emphasize, that I think what comes up as being interesting, in this case, the Heine-Borel theorem, comes up in a rather natural way. It's not just something that we, in a way that a program could find. It's not just something that we just judge for aesthetic reasons to be interesting. In fact, in a way, I think it's, from a purely aesthetic point of view, when you first see the Heine-Borel theorem, you think, well, who cares about open covers? It's a rather artificial statement. It's only because of this process of sort of arriving at that statement in a natural way that we see that it's interesting. So the things that I want to emphasize then are that what made the Heine-Borel theorem interesting was that just the very routine steps got a little bit stuck. So we can see in some objective way that it's a little bit harder than, for example, the fact that a continuous function preserves convergence. There is some process of isolating and abstracting out that difficulty, which I've just described, which is, I think, pretty automatable, at least in simple examples. There may be much more difficult examples where it's harder, but with simple examples, you can just automatically notice that you didn't need the intervals to be defined, that were defined to have anything to do with the continuous function that you were looking at. And once you've formulated the sort of lemma that you need, it's not completely trivial to prove, and it's useful in other contexts. So that's where centrality comes in. And another sign that something is central is that very often it has, and this seems like some mysterious thing, but it seems that very often results that have lots of applications also have lots of equivalent reformulations, or non-trivial equivalent reformulations. So when you start seeing results that have several equivalent versions, that tends to be a good sign that they're interesting and important. And again, though, that's something that I think is discoverable by a program in principle, not something that we have to tell the program. I'm not talking again about a program that exists yet, but something that I think could well exist in the not too distant future. So these aren't all of equal difficulty, but some other results that you would see in an analysis course that I think their interest can be justified in a similar sort of way as things that can come up when you try to solve problems that are just not quite routine anymore. So things like the nested intervals property, convergence of Cauchy sequences, and the other things listed here. You struggle once, you eventually manage to prove a result with the help of your lemma that you struggle to formulate and then prove. Once you've done that, if you abstract it sufficiently, then you find that you can apply it in many other contexts, and then you notch it down as an interesting statement that maybe is worthy of one day going into a textbook or something. Okay, I said I would say a bit more about how I think maths develops. This is a slightly fanciful picture, not to be taken too seriously, but it's, I mean, when I say fanciful, this is sort of how I would imagine, if there ever is an alpha zero, roughly how it would work. So what I don't think would happen would be that it would just start with some axioms and then just sort of arbitrarily work out consequences of those axioms, because you've got to filter it out. Otherwise, you just generate a whole lot of junk that's of no interest to anybody. And the vast majority of that junk will be statements that we wouldn't call mathematic. We just call it arbitrarily well-formed statements, but that's somehow not what we want. And we would never get to there'd be so many of them that we would never get to the sort of interesting theorems that we like to prove. So what can we do instead? Well, what I would suggest is that, a bit like what I showed you with the when I talked you through how program could solve something. We have a few, so I'm talking now about curly P. We have a few proof finding techniques, things like expanding definitions, but also other more sophisticated techniques than the ones I showed you. And we also have some statement generating techniques, and those are things like looking at special cases of existing statements, looking at generalizations and abstractions of existing techniques, or a more interesting one, which I'll talk about a bit more, is what I would call reduction. So you try to prove something. So it's the process that I talked about with the second example. You try to prove something, you get a little bit stuck, you formulate the thing that you need to unblock you, and you abstract away from that. So in other words, statements that arise naturally in the course of trying to prove other statements. I think that's a very important way that we generate new statements. So I'll say that a statement is generated by M using these basic statement generating techniques and proof generating techniques if you can find one of your statement generating techniques that applied to some subset of the statements in M yields this statement S, that it is judged to be interesting. It sort of passes our interest filters, which I've tried to describe a little bit. And if it turns out that using our proof finding techniques and not too vast a search, we can find a proof of that statement S, given appropriate background knowledge from M, not necessarily of the whole of M, but at least some of it. And so the idea is that we start with M0 will be some initial collection of statements, and I don't mean by that necessarily the axioms of ZFC, because I think that's not really how it works. Typically, a human mathematician will start with sort of a typical undergraduate mathematics education or something like that, which will have a lot more statements. So it'd be a vastly redundant system of statements. But I think that's important. So it might be that you could, with a program, you could start it off with just the axioms, but I'm not absolutely sure if you did that it would develop Euclidean geometry or something. It seems more likely that we only develop that because we live in the physical world and have various insights that come from there. So, and similarly with numbers, if you just started with set theoretic axioms, would you want to develop the numbers? I don't really know. So I'm assuming a much richer background than just axioms of set theory, just to be absolutely clear about that. So M0 is quite big. But once you've got that, I think a lot of things naturally follow from it. Okay. And what are the statement generating techniques? Well, I've basically mentioned all of them, although one of them I haven't explicitly mentioned. So the first three are things that Poyer talks about a lot in two books that I very much like. One's called something like Induction and Analogy in Mathematics. It's called something like The Methods of Mathematical Discovery. It's not How to Solve It, although it's got similar preoccupations. It's a 2-volume work that I like very much. I've temporarily forgotten the precise title. Anyway, he talks a lot about generalization, specialization, and analogy. So generalization, taking a statement and generalizing it. Obviously, specialization, taking a statement and specializing it. You've got a rather nice definition of analogy. Basically, statement A is analogous to statement B if they have a common generalization. You take statement A, you generalize it, you get something else, and then you specialize it and you get down to B. And very often in that case, if you know how to prove A, and you find a generalization of it, or you find a common generalization of A with some statement B, that can give you a lot of help if you're trying to prove B. And reduction is what I talked about. If you're trying to prove something, a lot of the time you will just go through the proof generating moves, and you'll reduce what you're trying to prove to something else, which will give you another statement. And then you can apply things like generalization and specialization to that other statement. And in that way, you have this sort of set of methods. So what I want to stress here is that the methods I'm talking about here of generating statements are not just things like take the conjunction of two statements that you've got. That would be a perfectly logically valid rule. And typically it's not very interesting. You know, if I say if I wrote a paper saying, by the way, Fermat's last theorem, the statement Fermat's last theorem and Semiratis' theorem is true because Fermat's last theorem was proved by Andrew Wiles and Richard Taylor, and Semeradi's theorem was proved by Semeradi, that would not count as an interesting statement. So because somehow just taking the conjunction of two statements doesn't count as a very interesting statement generating technique. So I'm talking about very different sorts of things from logically valid rules here. How much time have I got? Not that much. So let me just give a quick kind of picture of this development by telling a historically no doubt completely inaccurate construction of how, starting with a question a bit like this, we can end up with a whole lot of quite serious modern mathematics. So we start with a question like just a specific quadratic equation. After a lot of thought, if we, at a very early stage of the development of mathematics, we see that we can add 1 to both sides and get an equation of the form u squared equals 2, where u equals x minus 1. So we've reduced the original problem, which was solve a slightly complicated looking equation, to solving a simpler looking equation. But once we've done that, we find that we get a problem that looks very, very different in character from the problem we started with. Because somehow now when we think of solving a quadratic equation, what we really mean is reduce it to an equation of this form, that's solving by radicals. But if we want to say, how do we actually solve that equation, we might go through some sort of reasoning like this, that at least for the non-negative numbers, x squared is an increasing function, so we get that the square root of 2, should it exist, would have to be between 1 and 2, 1.4, 1.5, and so on. And we would say, that would give us the idea that we're actually generating a sequence of lower bounds that seem to be getting closer and closer to something. But if we hadn't yet developed infinite decimals, this would be provoking us to, we'd see we get a sequence of terminating decimals, and we'd start to think, well, actually, we could actually just think of this as defining us an infinite sequence, and maybe it makes sense to say that that infinite sequence is the square root of 2. So that is a big generalization of the sort of, it's a whole generalization of our number system to allow infinitely continuing decimal expansions. And then if we then ponder that a bit more, we look at sort of what, so we might say we don't really like this decimal representation. We'd like to think about it in a more abstract way. So we might start talking about the monotone sequences axiom. We've got these numbers 1, 1.4, 1.42, 1.414, and so on, getting bigger and bigger, but bounded above, and so forth. And if we then look at what we might say, well, why do we want to say that this infinite decimal is squares to 2? Well, because 1 squared and 1.4 squared, 1.41 squared, 1.414 squared, they get closer and closer to something. And we can sort of see why that is, because 1.414 is squared is very close to 1.415 squared. And we carry on reasoning like that, and we see that what we're really, we then do a process of abstraction similar to what I've talked about before. To isolate the property that we're really using about the function x squared, and that is continuity. We might at least temporarily think we need it to be an increasing function, then realize that actually we're not using that in a very profound way. And once we've done that, we've formulated the intermediate value theorem. So we've done a reduction of the problem, and then we've generalized to all continuous functions and so forth. And now let's consider a completely different but parallel development. We might notice that a sphere has some sort of resemblance to a circle. And when we sit down and try to work out what exactly we mean by that resemblance, we might say, well, actually, we can define a unit sphere around 0 using coordinates. That's a whole other story, why we have coordinate geometry, but let's just assume that as background in this way. And the sphere we can define in this way. And then we might say, well, actually, once we've done that, we could, if we wanted to, define an idea of an n-dimensional sphere, because we didn't really have to stop at 3 coordinates for this algebraic description, even if we can't really visualize what an n-dimensional sphere looks like. We can at least write down this algebraic formula very easily, and of course this is a very familiar story. And that raises the idea that actually we can have a whole subject of n-dimensional geometry. And actually I've called this a higher level abstraction because somehow we're thinking not just about how to generalize the idea of a circle and a sphere, but we're thinking about generalizing the whole notion of geometry. We can say, well, we could also generalize cubes, we're generalizing the notion of a sphere to other shapes, and surfaces can become 3D surfaces, etc., etc. And so there's some higher level of abstraction going on there, which would be, I think, a bit more challenging for a program while we're talking about that. But I don't see why it would be impossible to have a program that had sort of 3 or 4 levels of abstraction, which wouldn't be enough to be very powerful. There's also a thing that's very nice to do in a lot of situations, which is to try to generalize backwards. So it's not, before we started, it wasn't really obvious that it makes sense to talk about a 0-dimensional circle. So I'm calling this 1-dimensional because I'm thinking about the circle rather than the disk. And this is 2-dimensional, so a 0-dimensional circle. But once we've written it like this, we see that it's very natural to call it a pair of points. And we can think of it as this circle is bounding a disk, and so therefore the 0-dimensional or the 1-dimensional disk will be the interval that's bounded by that pair of points. So we can think of that as a specialization of the generalization, and it gives us our analogy. That's an example of Poyer's process in action. And once we've done that, we can then think, well, the intermediate value theorem, we've got an interval with 2 endpoints. An interval is just a one-dimensional disk. So how could we generalize the intermediate value theorem to a 2-dimensional disk? And when you've done that, and it takes a little bit of thought, but it becomes natural to formulate the Brouwer fixed point theorem. And at least some proofs of the intermediate value theorem you can then turn into proofs of the Brouwer fixed point theorem, and then you can end up into the world of simplicial complexes and simplicial homology, which, as we all know, has vast potential for generalization. We could end up with a huge portion of modern mathematics just from our starting point of trying to solve an innocent-looking quadratic equation and thinking idly musing about circles and spheres, and using, obviously oversimplifying the process quite a lot, but using standard statement generating techniques. Just a little bit more about how we filter out boring statements that we might generate using these techniques. There's a famous quote of Gowers about why he didn't completely like Fermat's last theorem, with this important qualification, as an isolated proposition. So just considered on its own, he had an attitude that I think a lot of modern mathematicians share, even those who were closely involved in the solution of Fermat's last theorem, that on its own it was not a completely interesting statement, because there are an awful lot of Diophantine equations that are extremely hard. And nowadays, I think the view, which I'm sure Gauss would subscribe to as well, was that amongst Diophantine equations, we tend to look for classes of Diophantine equations that are interesting for other reasons. So we want to have some form of generality. We know, of course, thanks to Matiasevich and Putnam, Davis, and Robinson, that there's no algorithm in general for solving Diophantine equations. And so we know somehow that if we just keep on trying to solve more and more Diophantine equations, they're just going to get harder and harder without limit, really. But there may be classes of them that are interesting for other reasons, as indeed there are. And another thing that is connected again with this process of how mathematics develops, we care quite a lot about feasibility. I think a lot of problems we regard as not totally interesting just because they're so obviously beyond what we could possibly do, that of course you can ask the question, but that's not an interesting question, because it's not a question that's going to provoke people to go and try and solve it. Maybe that's something that's not so easy for a program to judge, but I'm not quite sure why I say that, because there must be some reason that we're able to judge it. Okay, so just enlarging a little bit on that last point. So it quite often happens when you have a class of problems that you can hope that you will understand individual elements of that class sufficiently well that you'll be able to come up with an algorithm that solves a general member of that class. And we can do that for things like simultaneous equations and quadratic equations. And we can't do that for Diophantine equations. And we now know for very precise reasons that we can't do that. Here's a slightly less precisely defined class of, or less mathematically defined class of problems. That's Erdős problems. Those are an interesting intermediate case somehow. So a lot of those look like rather isolated questions, but turn out not to be, but they're sort of the statements of them are a little bit isolated, but very often they encapsulate some sort of difficulty in combinatorics. And it turns out that when you solve, particularly one of the more famous Erdős problems, you end up introducing techniques that lead to a whole cluster of problems being solved. And so they have a kind of generality that's a little bit hidden. So a recent example of that was the solution of a problem known as the sunflower conjecture. Not completely solved, but a very big advance was made on the sunflower conjecture using a new technique, which then turned out to lead to breakthroughs on a number of other problems. So I think one can class those problems as being interesting, despite their superficial appearances. So just to finish then, here is actually not the statement that I subscribe to. This is the statement that I've been arguing against. So I think that computers will not get good at proving theorems unless they're good at these processes of abstraction and singling out statements that are worth paying attention to. So I'm crossing that one out and saying the exact opposite, that in order to get any good at proving theorems, computers are going to have to be capable of doing the kinds of judgments that we do all the time. But the good news, if you're interested in automatic theorem proving, is that I think this is something that's possible in principle for computers to do. And I've tried to indicate that a little bit. And finally, maybe back on the pessimistic side, I mean, I think because of that, I believe that if we do get to this Aleph zero scenario that Akshay talks about, I think the idea that, and I'm not saying that Akshay suggests that this is what would happen. He's very agnostic about what would happen, deliberately so. But I know that some people think that what I've said at the beginning, that we would still have a role in telling the computers what to prove. I think that it's far from clear that we would have that role. I think computers might be perfectly capable of deciding for themselves what's interesting and convincing of us of the interest afterwards. So if that's the case, it's very hard to see how any of the sort of social structures that surround mathematical research can survive, and how anybody, I mean, it's actually quite a complicated thing. It still seems to me that it would be worth it for some people to put in the effort to understand mathematics well enough to understand what the computers could do. But it's not obvious what the social structures would be that would reward that sort of expertise. Maybe a little bit when it comes to training people to use mathematics in industry and things like that. Maybe there'd be some role in teaching, but I think, yeah, I think that sort of there would be a really huge impact. It's very, very hard to work out exactly how it would play out, which I think actually is again something that Akshay says. He also, I agree wholeheartedly with Akshay that it's very, very hard to say how all this would play out. But all I've tried to do is rule out one possibility for how I think it would play out, and I will stop there because we probably want to have some questions.